the hands go waving goodbye. No, I get so forgetful when I look in your eyes. The time go, it's starting to fly.
Hello everyone, today I'll be starting off our demonstration video with a quick introduction. Our experiment focuses on something we deal with every day in our life, which is equilibrium and LCP. I know it sounds very complex, but we found a really simple way to see it happen in real life by just using water, ice cubes, and some common things you can find at home. In chemistry, equilibrium is a balance, meaning that the forward and the reverse reaction happens at the same rate. What's so fun about this is that this balance can be shifted by temperature, concentration, and pressure. In this experiment, we used carbonated drinks and added things like vinegar, lemon juice, ice, and hot water to see how the system reacts to the change. Come, let's get started.
Hi, now I'll be telling you about the objectives of the experiment. One of the objectives of the experiment is to learn the concept of dynamic equilibrium in chemical reactions. Next, it is also used to predict how changing temperature, concentration, pressure, or adding a catalyst shifts chemical equilibria using the chateliers principle. Not only that, but it is also used to examine the equilibrium constant K and its role in describing chemical equilibrium. Last but not least, the objective of the experiment is also used to identify the presence of ion, which is acetate ion, affects the ionization of a weak acid, which is acetic acid, and modify the pH of the solution.
The first hypothesis of this experiment is to examine the influence of concentration and temperature on chemical equilibrium, and the second hypothesis is to find the equilibrium constant.
For part A, effect of temperature, we are leveling 2 bottles of carbonated drinks as A and B. Now we are shaking and observing the bubbles formed in both bottles. Then we put bottle B in ice bath and bottle A in hot water. We keep them for 5 minutes. After 5 minutes, we observe the bubbles form in both bottles and compare before and after formation of the bubbles for both conditions. This part, we choose only one bottle, which is bottle B. We shake it well and observe bubbles formed. After that, we squeeze a lemon, then open the cap of the bottle and pour around 2.5 milliliter of lemon juice in that bottle, and we closed the bottle immediately. We also observed and recorded the bubbles formed. For part C, effect of pressure, we choose bottle A. We gently shake the bottle and observe the bubble formed. After that, we opened the bottle cap and filled the carbonated drink into a clear drinking glass. We recorded the observation for a while of how much bubble formed after pouring the carbonated drink into the glass.
Chemical equilibrium and Chateliers principle aren't just chemistry concepts. They happen all around us every day. For example, when you open a soda can, the pressure drops and the carbon dioxide gas escapes, shifting the equilibrium. When you bake a cake, heat causes baking soda to release gas, making the cake rise again, a shift in equilibrium. Even in your body, during exercise, more carbon dioxide is produced, so your body shifts the chemical balance and makes you breathe faster to remove it. Whether it's cooking, breathing, or even cleaning with soap, these reactions adjust to changes in temperature, pressure, or in concentration, just like Lee Chatelier predicted. It's amazing how science silently works in the background of everyday life.
Lee Chatelier principle was observed in this experiment. The principle states that when the conditions of a system in equilibrium are changed in the system, reacts to counteract the change and re-establish equilibrium. The equilibrium is disturbed when any of the reactants or products are disturbed. As well, we can see that the data we have collected from both experiments, part A, B, and C, both confirm that Lee Chatelier's principle were indeed correct and applicable. As the principle states, when the different substance were added into the carbonated drinks, the equilibrium had shifted accordingly in order to gain balance again. The shift in equilibrium results in a change of the bubble formation for each mixture.